Okay, so I think it's time for us to get started. All right, so this class we're going to continue on the sulfur dioxide control devices for mainly about the design problems. So as I said in the notification, so this class we have to do a little bit more complicated calculations here. So that's why I asked you guys to bring a calculator. But you can also use one on your computer or on your cell phone if you feel comfortable with that. All right. So just as a recap, so last class we mentioned that for the sulfur dioxide control, it mainly uses some raw materials to neutralize acidic gases, right? So we can use limestone scrubbing. So basically, we introduce these what we call slurry, or a mixture of solid and liquid into the spray tower to generate tiny droplets. While at the same time, we introduce a flue gas into the reactor here. And then because of the contact between the gas and the droplet, there's going to be reaction, and the acidic gases will get neutralized from this process, right? And then generally, we'll also introduce oxygen at the bottom, mainly because the product coming out of this process, this reaction is going to be calcium sulfite, right? Calcium sulfite is not stable enough. And also the solubility is still a little bit high, right? So that's why we introduce oxygen to convert to calcium sulfate, which has further lower solubility. And then we can further compress it, dry it, and then form the gypsum, which is a raw material for construction, right? So this is a way we, this is how we basically control these sulfur dioxide or other acidic gases, right? So we also mentioned a few questions, right? So if we already know the amount of sulfur dioxide that needs to be controlled, similar to the problem or the team project you're working on right now. So based on the co-composition, you can calculate how much sulfur dioxide you can generate from this combustion process. Then how do we calculate the limestone feed rate? Okay, so here I'm listing this question again. So we briefly introduced that in our last class, but let's here do a quick calculation. So I'll launch a quiz. So if we know that we need to control 32 tons of sulfur dioxide per day, then how much calcium carbonate do we need to feed? Okay, 10 more seconds. Okay, we'll stop here. So the correct answer is 50 tons per day. So we give a very simple solution to this question. So we were assuming that first, let's not look at the tons here. Let's assume that there are 32 grams of sulfur dioxide. So 32 grams of sulfur dioxide means it's 0.5 moles of sulfur dioxide, right? And we know that sulfur dioxide react with calcium carbonate at a 1-to-1 ratio. So we form calcium sulfite and carbon dioxide, right? So they're at a stoichiometric ratio of 1-to-1. So what that means is if we want to neutralize 0.5 moles of sulfur dioxide, then we need 0.5 moles of calcium carbonate. Okay, so the molecular weight of calcium carbonate is 100 gram per mole, right? So what that means is we need 50 grams. So 32 grams of sulfur dioxide needs 50 grams of calcium carbonate, right? So that's why 32 tons of sulfur dioxide needs 50 tons. Okay, so this is a very simple stoichiometric ratio question. So if we know at which molecular ratio they're reacting, then we can calculate, we should be able to calculate how much of the calcium carbonate we need. And this is a general question we're going to face for the sulfur dioxide control, or the either the wet scrubbing or the dry scrubbing process. So we're interested in two questions. So the first question is how much raw material we need to feed, right? For example, how much limestone we need. And the second question is how much slurry will form. How much sludge. Right? For the sulfur dioxide design, sulfur dioxide control design, we're mainly interested in two questions. One is how much limestone should we feed into the system? Either limestone, lime, or trona, all the raw material that can neutralize these acidic gases, right? And the second question is how much product we're forming, because finally we need to transfer this product to somewhere else. If we don't know the quantity of or production rate of this product, then we cannot design the system, right? So here the limestone is a raw material or the reactant. The sludge is basically what forms at the bottom of this reactor, right? So it's going to be composed of water, going to be composed of calcium sulfate, right? And then of course the reaction is not complete generally. So there is still going to be some calcium sulfide that's being remained, or the calcium carbonate, right? So the sludge is going to be a mixture of all of these chemicals, okay? So these are the two general questions, and we can use a similar idea to understand what is happening here. So let's say right now we assume that 32 tons of the sulfur dioxide is being neutralized. What that means is that we need to provide 50 tons of the calcium carbonate into the system. But unluckily, the limestone is not purely composed of calcium carbonate. So there's always some impurities in the limestone there. So there are going to be a little bit more complexity in here. And let's, for now, if we assume that the limestone is purely composed of calcium carbonate, then based on this relationship, then we can calculate how much of the calcium sulfate we're going to form from this process, right? We know that everything is reacting at a stoichiometric ratio of 1:1. So what that means is we're going to form 0.5 moles of the calcium sulfate, right? And then if we know the calcium sulfate mass, then we can calculate how much of the sludge we're going to need, okay? So everything is still based on the stoichiometry, but due to the impurity of the limestone, and also we always need to basically provide more limestone into the system to completely neutralize these acidic gases. So the situation will get a little bit complex. So here, what I'm showing is an actual design system. So I mentioned in our last class that in your design problem or team project, you also need to come up with this table here, right? That will basically give an overview of what is the composition of the flue gas from this co-combustion process, right? And then further, based on the composition of the sulfur dioxide and hydrogen chloride, we should be able to calculate what is the limestone we need in the entire system, okay? So again, I'm listing the two questions or the two problems for this sulfur dioxide scrubber design problem. So the first is the limestone feed rate, and the second is the sludge production rate, okay? So these are the two questions that we have to deal with. So under actual situation, we cannot assume that the limestone is pure calcium carbonate anymore. Okay, so if you look at the composition here, the limestone is generally composed of 94% of the calcium carbonate, 1.5% of the magnesium carbonate, and there are some inert materials. Okay, but this shouldn't affect the solution a lot because we're not letting these acidic gas to react with calcium carbonate. We're actually letting them to react with the carbonate ions, right? So it doesn't matter whether it's calcium carbonate or whether it's magnesium carbonate. So as long as we know what is the carbonate it needs for this neutralization process or neutralization reaction, then we should be able to relate that to the limestone. Okay. You see, the second point is that generally we'll provide more limestone into the system, which is 1.1 times of the stoichiometric ratio, right? Basically, we'll provide 10% more of the limestone into this scrubber so that it can more completely react with acidic gases, right? So let's say that we further assume that the removal efficiency of the sulfur dioxide is 90%. And for the hydrogen chloride, there's a complete removal. Okay, so these are the assumptions that were made onto the this reaction here. Then let's say, how do we calculate the feed rate of the limestone? Okay, so I think maybe we can put some thoughts on this problem for a little bit. I don't want to directly write down the solutions for this problem. So the general idea is we know, let's say we know what is the sulfur dioxide or hydrogen chloride that we have to control. And we further know that for these sulfur dioxide, we cannot remove everything. We assume that we just removed 90% of the sulfur dioxide here. But here, for the hydrogen chloride, we remove 100% of them, right? And then basically these acidic gas will react with the carbonate ions, right? And basically get neutralized. And these carbonate ions are being provided by the limestone. Okay, and we know that the limestone is further composed of calcium carbonate, magnesium carbonate, and inert. So the question is asking us, what is the feed rate of the limestone? Okay, so maybe we can put some thoughts on this and look at this problem for maybe 1 minute or 2 minutes, and then we can start to discuss this. All right. Okay, I think we can start to analyze this problem. All right, so for these sulfur dioxide control design problems, we need to understand what is our target and what is the reality, right? So basically the target is to neutralize these acidic gases, right? And we know that for these for this problem, we need to neutralize hydrogen chloride and sulfur dioxide. Okay, and we're trying to use carbonate ions to neutralize these species. Okay, so that's why in order to calculate the limestone feed rate or the amount of limestone we need to first know what is the amount of the acidic gas. Okay, so for this problem, it already provides you what is basically what is the flow rate or the rate of generation for these acidic gases. We can quite easily calculate that. And you notice that here the units are in the US units or the British units, right? So for simplicity, let's convert it to the standard units first. Okay, so basically we can calculate what is the flow rate of the sulfur dioxide. Okay, so that's 31,080. And then our goal is we want to neutralize 90% of them, right? And we'll convert this into kilograms, which is 0.45. This is kilogram per pound. And then here the unit is pound per hour. Okay, so that's 12587.4 kilogram per hour. Okay, so if you have a calculator, I think now is also a good time to check whether these answers are correct. All right. So this is the amount of the sulfur dioxide we need to control. I mentioned that it's being reacted at a rate of or efficiency of 90%, right? And then we also need to control the hydrogen chloride, which is 432 multiplied by 0.45. That is 194.4 kilogram per hour. So basically, this is our target. We have to control these acidic gases, right? And then we mentioned that to neutralize these acidic gases, we're using carbonate ions, right? So based on their mass flow rate, we should be able to calculate what is the molar flow rate of the carbonate ions it needs for the reaction, right? So we know that the sulfur dioxide react with the carbonate ions at a stoichiometric ratio of 1:1, because we're forming sulfide ions, carbon dioxide, right? And then two numbers of hydrogen chloride will react one number of the carbonate ions. Okay, so this is a reaction for the hydrogen chloride and the carbonate ions. So we have these two reactions. So what this means is that in order to neutralize 1 mole of the sulfur dioxide, we need 1 mole of the carbonate ions. And in order to remove 1 mole of the hydrogen chloride, we just need 0.5 mole of the carbonate ions, right? And since we already know the mass, we can calculate what is the carbonate ions it needs to remove these acidic gases. Okay. So we can calculate what is the carbonate ions that it requires for each hour. So for the sulfur dioxide, and because of this reaction here, we know that it's going to be 125. Let me list out the equation here. Right, simply because the sulfur dioxide reacts with the carbonate ions at a stoichiometric ratio of 1:1. So the moles that's required for the sulfur dioxide. Sulfur dioxide is just the mass flow rate divided by its molecular weight, right? So that's going to be 12587.4 divided by 64 grams per mole. All right. So you can find out that this is 196671 mole per hour. So this is how many moles of the carbon ions we need to neutralize the sulfur dioxide. Okay. And similarly, we can calculate this amount for the hydrogen chloride, which is MHCl. And then we'll divide this value by 2, mainly because there's 2 moles of the hydrogen chloride will be able to remove, will be able to react with 1 mole of the carbonate ions, right? So that's going to be 194.4. Okay. So basically, based on the flow rate of the sulfur dioxide and hydrogen chloride, we can calculate what is the amount of the carbonate ions we need to neutralize these gas species, right? So the total required, say we'll move here. So the required carbonate ions is just going to be these 2 numbers added together. Okay, so this is the required carbonate ions it needs to neutralize these gas acidic species. And then further in this problem, we assume that we will provide 10% more of the limestone, right? So what that means is that we need to provide actual carbonate ions into this calculation. So the actual carbon ions that's needed by this reaction is going to be 199,328 multiplied by 1.1. Okay, so that's going to be 219,261 mole per hour. Okay, so this is the actual amount of the carbon ions that's required from this reaction. Okay, so this is our target. What this means is that in order to react with all of these acidic gases, it requires this amount of carbonate ions to go through the reaction, right? And then what is the reality? Because we need to match the target with the reality, right? So the reality is we're going to use limestone. Let's say that this is our limestone, okay? So we're going to use the limestone to neutralize, or to use the limestone to provide these carbonate ions to neutralize the gas species. So we mentioned that the limestone is not pure. It contains calcium carbonate, magnesium carbonate, and 4.5% of the inert species, right? So we can use this bar to show what that means, right? So let's say 94% of them are calcium carbonate, and 1.5% is magnesium carbonate. And then we have 4.5% of the inert. Okay, So we're using this limestone to provide the carbonate ions to neutralize the acidic gas species. And because of that, we need to know what is the amount of the carbonate ions it can provide for this standard unit of the limestone, right? So for simplicity, what we can do is we can assume that we're trying to analyze 100 grams of the limestone. And we need to calculate how much carbonate ions it provides to the reaction, right? So if you assume that there's 100 grams, then what we can directly know is that there are going to be 94 grams of the calcium carbonate, right? And then 1.5 gram of the magnesium carbonate, and then 4.5 grams of the inert. Okay. And if we know the mass of the calcium carbonate, we can calculate what is the moles of the carbonate ions it provides to the reaction, right? So it's just going to be 94 divided by the molecular weight of the calcium carbonate, right? So that's going to be 94 divided by 100, which is 0.94 mole of the carbonate ions. And in terms of the magnesium carbonate, we'll use 1.5 divided by the molecular weight of the magnesium carbonate, which is 1.5 divided by 84. That's going to be 0.0178 mole. Okay, so basically, what we're trying to do is we're trying to analyze 100 grams of the limestone. Within 100 grams of limestone, how many carbonate ions it provides, right? So what this means is that we need to add these up together to calculate the moles of the carbonate ions, right? So that will give you 0.957 mole of carbonate ions. Okay, so let's see the problem here. So we know that to neutralize the acidic gases, we need this amount of the carbonate ions. And we know that for 100 grams of the limestone, we have this amount of carbonate ions. And then we can use this relationship to relate to the total required amount of the limestone, right? So that can be calculated by limestone equal to 219,261. Okay. So what this means is that we'll divide this total required carbonate ions by the carbonate ions that's provided by 100 grams of the limestone. And then we multiply that by the mass of this limestone here, right? So this is going to be the total amount of the limestone we're going to need. And if you use your calculator, you can find out that this is going to be 22,911 kilogram per hour. Okay. So I think there are quite many steps of calculations here. But the general idea is that we're using the carbonate ions as a link between the acidic gases and the limestone. Okay, so if we know the generation amount of the acidic gases, then we can calculate what is the amount of ions for this reaction. And if we know the amount of carbonate ions, then we can relate this to the amount of limestone that's required for this reaction, right? So that's why we separate this into the target here, and then reality in here. Okay, so let's just go through this process again. I know that there are quite many calculations here. I think you also have a homework problems on this similar type of questions. I think you will get more practice in here. I admit that this is indeed quite complex, but the general idea is that we're trying to use the carbon ions as a bridge to calculate this process. Okay, so we can separate that into multiple steps. So the first step is to find out how much acidic gas we need to deal with. Okay, so that's generally given by the table or by the question there, right? Similarly, we can calculate what is the amount of sulfur dioxide we can generate from the coal-fired power plant. So that's already known, right? So the first step is try to see how much of the acidic gas we're trying to deal with, right? And the second step is convert the acidic gas amount into the carbonate ions it requires to react. Because if we know the amount of sulfur dioxide, we should be able to know how many carbonate ions it reacts, right? Because it reacts at 1-to-1 ratio there. And the third step is to calculate what is the actual carbonate ions it requires, right? We mentioned that it's going to react at 10% more of the limestone, right? So that's why we multiply that by 1.1, basically, to add this actual limestone. And this is the actual carbonate ions it requires to neutralize the acidic gas, okay? And the fourth step is to find out how many carbonate ions can be provided by the limestone. Here we're using an example, 100 grams of limestone. We can calculate what is the weight of the calcium carbonate, what is the weight of the magnesium carbonate, and then calculate the carbonate ions, right? And finally, the fifth step is to relate this carbonate ions amount and then calculate what is the total mass of the limestone, okay? So this is where we calculate the feed rate of the limestone. So everything is based on the stoichiometric ratio. And I would say that you're going to use the same method for your dry sorbent injection. Right? Let's say we're introducing trona into the system or introducing lime into the system, right? We know that the lime is not pure calcium oxide, right? So there's always some other chemical species, for example, sodium oxide, right? Or sodium carbonate. So you need to find out what is the chemical composition of the lime, right? And basically the lime will react with the acidic gases, similar to the ratios that are provided here, right? For example, I think we also have the reactions here, okay? So basically it's reacting with the oxygen negative ions, right? Or you can think of that as the hydroxide ions. Okay, so based on these reactions, you can find out what is the required oxygen ions or what is the required hydroxide ions and use that as a bridge to relate the amount of the acidic gases and the actual required amount of your either lime or trona into the system, right? So this is how we solve the feed rate of the limestone. We mentioned that for the design problem, we're also interested in what is the sludge production rate. Okay, so the sludge is just the the product that's coming out of this reaction, right? So we mentioned that if we consider the product, So that's going to form calcium sulfite first. And then finally, we're going to form calcium sulfate, mainly because we add oxygen into the system, right? We oxidize these calcium sulfite. And you see that in this problem, we're basically providing more limestone into the scrubber. And because of that, the sludge is also not going to be a pure substance, right? And we need to consider that there are also inert in the system, right? So what we can do is we can also draw a bar that's similar to this limestone bar here. So let's say that we're trying to analyze 100 grams of the sludge, or the product coming out of the scrubber. So you see, for this question, it assumes that 60% of the mass is water, right? So from this bar here, we know that actually 60%. We don't need to consider that. So that's going to be just pure water, okay? And the remaining 40% are going to be the solid, okay? And further, if we consider the solid composition, it's actually made of quite many things. So first, we have a proportion of the limestone that are not being reacted. So remember, in this problem, we assume that we provide 1.1 times of the amount that's required by the stoichiometric ratio, right? So that 10% extra are not being reacted. So we can say that this amount is unreacted, okay? And then for the reacted limestone, we know that there is further a fraction that's inert, right? And then we have a fraction that's calcium sulfate, and then we have a fraction of magnesium sulfate. Okay, so to calculate what is the total amount of the sludge, we need to analyze basically piece by piece and add them all together, right? So for this problem, let's also basically try to solve it or target at it one by one, okay? From the previous problem, we know that the total amount of limestone is going to have this value here. And we know that it's basically 1.1 times of the amount that's required by the stoichiometry. So we can first calculate what is unreacted limestone, okay? So the unreacted limestone is going to be 22911 multiplied by 0.1 divided by 1.1, okay? So we mentioned that among this 1.1 total amount of the limestone, basically 1 is being reacted from this process, and 0.1 is just extra, right? So this is going to be the unreacted fraction of the limestone. And you can find out that this amount is 2083 kilogram per hour. Okay, so this is the MUR. And we should also write out these reacted, inert. And this is for the magnesium sulfate, that's going to be reacted magnesium sulfate. And here we have reacted calcium sulfate. Okay, so the total amount should be all of these added together plus the water. Okay, so that's going to be the production rate of the sludge. So we first calculated what is the unreacted limestone here, right? So if we can calculate what is unreacted limestone, we can also calculate what is a reacted limestone. So we can use a similar method. Okay. So we can use a similar method and then just multiply this 22911. and then multiply by 1, divide by 1.1. Okay, so this is a reacted amount of the limestone. And that's going to be 20828 kilogram per hour. All right. And then if we know the reacted limestone, then based on the assumption that 94% of them is calcium carbonate, 1.5% is magnesium carbonate, then we can calculate what is the reacted amount of calcium carbonate. So that's going to be 2092828 multiplied by 94%. And similarly, we can calculate what is the reacted amount of magnesium carbonate. And also the inert. Okay. So in terms of the inert, its composition is not being changed, right? So it's just going to be the amount that's going to fill in this pie here. Okay. And in terms of the calcium carbonate and magnesium carbonate, their composition changed. So their composition changed to magnesium sulfate and calcium sulfate, right? And since we already know the mass of them, then we can convert them first into the rate in moles, and then further convert the rate in moles into the mass, right? So we know that the calcium carbonate get converted into the calcium sulfate. Because of that, the production rate of the calcium sulfate is going to be the mass flow rate of the calcium carbonate divided by its molecular weight and multiplied by the molecular weight of the calcium sulfate. So that's going to be 19578 36 divided by 100. Okay, so you can get 26626 kilogram per hour. Okay, and we can do the same for the magnesium sulfate. Okay, so now we have calculated all the terms that's required for this sludge. Okay, so first we know what is the water, right? And then we calculate what is the unreacted amount of the limestone. And that's basically the pie chart here. So this is the actual amount of limestone we provide to the scrubber, right? And then we were able to calculate what is the inert that's in the reacted limestone. So that is this amount here, okay? And then in the reacted limestone, we were able to calculate what is the formation rate of the calcium sulfate, right? The calcium sulfate is here. Okay, so finally we have the magnesium sulfate, which is here. Okay, and these are calculated based on the reacted amount of the limestone here. Okay, so now we can just add everything together. So first we can calculate what is the total solid in the sludge. So that is going to be the unreacted limestone plus the reacted limestone and the inert inside, and then the reacted limestone magnesium sulfate and the reacted limestone calcium sulfate. Okay, so that's going to be 30093 kilogram per hour. Okay, so finally, if we want to calculate the total mass of the sludge, we need to know that the solid actually just occupies 40% of the total sludge. Water occupies 60%, right? So what we need to do is to use the solid mass divide by 40%. And that is 75233 kilogram per hour. Okay, so this is a total sludge. All right. So this is, I think this is indeed a quite complex process, right? So you see that we use the entire class to do these calculations. I'm not sure if you were able to catch me in typing the calculators there, but definitely in the homework and in the team project, you need to go through these detailed calculations to find out what is the design parameters, right? So as we mentioned, we're just interested in two parameters for sulfur dioxide control. So one is the limestone feed rate, or I should say it's just the raw material feed rate. It can be lime, trona, limestone, and so on, right? And the other is the sludge production rate. That is the product you generate from this reaction, okay? Mainly because if we know these feed rates, then we can design other auxiliary systems or accessory systems to transport these raw materials and products. So we mentioned that for the feed rate, we're using the carbonate ions as a link, right, to convert the amount of the acidic acids to the required calcium, to the required carbonate ions, and then convert that required carbonate ions into the limestone feed rate. And as for the sludge production rate, I think it's more straightforward if we can divide this sludge into different sections, right? And then just calculate the format or the production rate of each component one by one. Okay. So again, we're trying to use this this reacted limestone, right, to convert it into the reacted calcium carbonate and magnesium carbonate, and further into the calcium sulfate and magnesium sulfate. Okay, so I would suggest that please do go through this calculation process and let me know if you have any questions. I know that the complex can get very complicated here. Okay, so if needed, we can just go through this process again in our next class, but I don't think you guys can bear with all of these calculations here. So just let me know if you have any questions. That's all for this class.